In this video, we're going to talk about a couple examples in lab number 10. Lab 10 is all about paired tests. So how do we compare samples that have resulted from a paired design? And usually we want to use a t-test when possible. And we have the paired t-test variation. But when we do not meet the requirements for the t-test, the paired t-test, we have the Wilcoxon signed rank test as a backup. So the code for this in R is very similar to what we saw in the previous two labs. T.test, Wilcox.test. But in order to indicate that there is a paired design, we need to indicate that. And additionally, if you have a directional alternative hypothesis, that can be specified in addition to the paired indication. So let's look at example 1, which asks us to compare these upper and lower data sets. And what we've got here are the median stream substrate particle sizes in upper and lower reaches of 16 randomly selected streams in the Henry's Fork watershed. So here there's 16 pairs, but they are pairs because each stream had an upper and a lower value. So it's like you're getting a pair of data from each individual. So therefore, we might be able to assume that the upper and lower values are not independent, therefore they are paired. So we do not meet the requirement to do a regular two-sample t-test because the data are paired. But we'll see in a moment here that we also cannot do a regular two-sample t-test for another reason. Okay, well, we've got paired data. We would like to do a paired t-test. One of the requirements for the paired t-test is that the differences are either normally distributed or have a sufficiently large sample size. But as we can see here, the number of pairs is a 16. So therefore, since the sample size is not particularly large, we need these differences to be normally distributed. So let's calculate these differences. I'm going to name a vector. I'm going to call it diff, and I'm going to do the upper values minus the lower values. Of course, I need to use that $sign. Okay. And I just noticed a typo, so here we go. Those are our differences. It's a vector, right? We want to check, are these differences normally distributed? I like to do the QQ plot because it gives us a visualization of whether this data set appears normally distributed. And it doesn't look too bad, right? It follows that approximate straight line. So visually, okay, looks pretty normal. But let's go and lay down the hammer with the Shapiro test of the differences. I want to see a big p-value, right? Because I want this to indicate that the sample is normally distributed. That's awesome, right? Because if that wasn't big enough, then we can't meet the t-test requirement. Okay, the differences, thus, the differences are approximately normal. So now let's do the paired t-test. I'm going to scroll on down here. The hypothesis for the paired t-test, I've got some examples of how you would write that over here, so I'm not going to just retype that. So another way that you can consider the null hypothesis is that the population mean of the differences in the stream substrate particle sizes is 0 between the upper and lower reaches or sections. So here I just wanted to give you another option of the way that these hypotheses can commonly be expressed. So 3 options here. Okay, let's do this paired t-test. The code or the command is t.test, and I need to enter our upper and our lower data sets. So we don't actually type in the differences. We are going to use upper, comma, lower. I'm being a little lazy here. I'm going to replace that minus with a comma. But I'm not done, because if we hit enter right now, it's not going to recognize that these are pairs. It needs to know that these 2 values are a pair. That's the 16th pair. That this is the 13th pair. It needs to know that. And we indicate that by saying paired equals, I think you could just say t, but I like to write true to be super complete. And take a look at your output here. Make sure it says paired t-test. And just like in our other t-tests that we've seen, it shows you the test statistic, the degrees of freedom. That one is not hard to figure out, unlike with the regular t-test. The regular t-test degrees of freedom is a crazy town. This degrees of freedom is just 16 minus 1 from up here. 16 minus 1. And then at the end of the day, we're just looking for that p-value. So that p-value is small, right? So we will reject the null hypothesis since the p-value is less than 0.05. And that's iterated over here. This indicates that there's evidence that the mean difference between the upper and lower sections of the streams is not 0. Right, so there is evidence for the alternative, which said not 0. Also, look at that confidence interval. Right, that's the confidence interval for the mean difference. And it is about a 5.01 comma to a 42.42. That's nice. And so does this interval contain 0? No, right? Does not contain 0. Indicating further support that a difference was observed. So that supports our conclusion to reject the null hypothesis. So that's the paired t-test. T.test, don't forget, paired equals true. The second portion of this example asks you to use the regular t-test. Boop. In violation of what we had mentioned, right? If you do the regular t-test, it is not, I should say, the conditions for the regular t-test are not met. Because 1, we have paired data. 2, I neglected to do this a minute ago, but the Shapiro test for the upper data set has a small p-value. The Shapiro test for the lower data set also has a small p-value. So the regular t-test should not be used because we have paired data and these samples are not normal with small sample sizes. But R doesn't know any better. If you did t.test and you asked it to just crunch the numbers, it will crunch those numbers. And check this out. It gave us a big p-value, which is different than what the paired test gave us here. So we don't know what's the correct conclusion. We don't know which test gave us the incorrect conclusion. But it's very likely that using the wrong test likely ended up in an error, which would be a type 2 error in this case. Okay, well that was fun. That's going to conclude this video.